Okay, so this is the start of our video lecture for Chapter 15, Section 9, which covers the Le Chatelier's principle. This section starts on page 703, and that very first page has a brief description of Le Chatelier's principle. So, definition of Le Chatelier's principle: when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. So what does that mean? That means if you have a reaction at equilibrium and you do something to make the equilibrium go away, or equilibrium is no longer there, maybe you're adding products or adding reactants or changing volume, the reaction is going to shift to reestablish equilibrium. Because if you add more reactant, you're no longer at equilibrium. So in the book, it talks about neighboring countries A and B, and if you have similar populations in each, you're not really going to have people moving too much. But let's say in country A, you have a huge increase in populations. There's too many people in country A. What's going to happen? Well, they see country B right there, and they'll move to country B. Likewise, if country B has a huge increase in population, too many people in B, it's overcrowded, you can't get jobs. What's going to happen? People in country B see country A that isn't very populated. It looks fabulous, and they move over to A until equilibrium has been reestablished, or you've got similar amounts of people in both countries. So read page 703, does a better job describing it than I did. And then, so pause, read page 703 to 704, and then hit play, and we'll continue on. Okay, so thank you for reading that first page in section 9. What I'm going to do now is to look at a general reaction. So where we have reactants, which will react in the forward direction, make products. And again, it's an equilibrium reaction, so I know I've got products that can react to make reactants. So it's important to remember, just because we say it's a product does not mean it's not going to react and form more reactants. Product just means, or just refers to the chemicals on the right-hand side of the equilibrium arrows. Reactants are the chemicals on the left of the arrows. Again, I've got forward reaction. I have a reverse reaction. I know at equilibrium, the rate of my forward reaction equals the rate of the reverse reaction. Couple definitions. If I say the reaction shifts to the right, that means it's going to the right, which, let me get a color, is blue. So to the right means I'm using up my reactants and going in this direction to make more products. So if I shift right, I use reactants, I make more products. That means my concentration of the reactants goes down, right? If I'm using up the reactants, they're being consumed, their molarity would go down. Shifting right, what happens to the products? You're making more products, so the concentration of the products increases. So again, right shift, use up reactants, make new products. A left shift, use products to make more reactants. So I'm going in this direction. I'm going to use up my products to make more reactants. So if I'm shifting to the left, what happens to the concentration of reactants? You're making more reactants, so the concentration of reactants will increase. What happens at the concentration of products? I'm shifting left. My concentration of products decreases. So these are definitions, terms, concepts that we need to know and remember. Now we're going to look at if I apply a stress to a system at equilibrium. Applying a stress just means you're disturbing equilibrium. You could be adding reactants, you could be adding products, you could be removing reactants, you could be removing products. You could change the volume of the container for a gaseous reaction. We'll look at many examples of the stress, but we're going to start with adding reactants. So let's say right now I've got an equilibrium reaction between R and P, and I'm at equilibrium. That means I've got a forward rate equal to the reverse rate, and that's it. But if I add reactants, I'm no longer at equilibrium, right? I was at equilibrium before. Adding more reactants, I'm not at equilibrium. You could determine that if you were to solve for your Q or your reaction quotient. You'd see it's not equal to K. But for Le Chatelier, it's just conceptual. So adding reactants I'm no longer at equilibrium. What shift? What's going to happen? How will the reaction reestablish equilibrium? So what I like to think about is before I added R, I was at equilibrium. It's kind of like the lowest energy state of the reaction, or where the ratio of reactants to products likes to be as determined by that K value. So if I'm adding more R, I have too much R in my beaker. So how do I get rid of R or decrease R? I shift to the right. So if you add R to reestablish equilibrium, the reaction will shift to the right. That's going to use up reactants to make more products. How about if I remove reactants? So if I remove reactants, that means I've got too few reactants in my beaker. I'm no longer at equilibrium. The system will shift to reestablish equilibrium by making more R. So how do we make more R? We're going to shift left. So by shifting left, the reaction will use up P, it will decrease, and make more R. Same idea, if I add P, so if I'm at equilibrium, I then add more products, whatever they happen to be. You have too many products, so that reaction needs to use up products to make more reactants. So what do you think we're going to do? Use up products, make reactants, shift left. So essentially, if you add anything to the right, it shifts left. If you add anything to the left, it shifts to the right. Lastly, if I remove products. If I remove products, I don't have enough products, I need to make more. How do I make more products? Right here, and I shift to the right. So if I remove P, I don't have enough products, I need to make more products by shifting right. So this was kind of like a good summary slide of what happens if you add or remove reactants in products. And hopefully through this discussion, you understand why the reaction will shift to the right or the left, right, to reestablish equilibrium. Do not just try to memorize this. Okay, so we're going to go ahead and take this concept and apply it to our practice exercise 12. So we're given a reaction PCl5 in equilibrium with PCl3 and Cl2. And we're given a delta H value. So delta H is covered in Chem 101. I see that this is a positive delta H, so that's kind of light. A positive delta H, so we'll remember that's endothermic. Sorry, I'm terrible at writing with this mouse. Endothermic, and I know if I have an endothermic reaction, that means that I have to put heat in to make the reaction go. So if I'm applying heat to make the reaction go, heat is a reactant. So write that down. So heat is a reactant, so I have heat as a reactant, then plus. So I think my two reactants are heat and PCl5. My two products are PCl3 and Cl2. And we want to figure out in which direction will the equilibrium shift when A, Cl2 is removed. So if I'm removing Cl2, that's a product. If I'm removing Cl2, I have too few products. How do I make more products? That's right, we're going to shift to the right. So by shifting to the right, I'll use up PCl5 and I'll make more PCl3 and Cl2 until equilibrium is reestablished. B, the temperature is decreased. So we decided delta H is positive, endothermic, apply heat. Heat is a reactant. Decreasing temperature is removing heat from that reaction. So if I remove heat, I'm removing a reactant. I have too few reactants. So to reestablish equilibrium, I need to make more reactants, which means I will be shifting to the left. C, the volume of the reaction system is increased. Okay, so when we're looking at volume of the reaction, that I need to focus on my gaseous reactants and products. So on the reaction, I see I have 1 mole of gas for the reactants. And for the products, I have 2 moles of gas. So again, if I'm changing the volume, that only affects gases because gases change volume based on the size of their container. So when I'm thinking about changing the volume, I think about right now when my reaction is at equilibrium, there's an equilibrium pressure. If I increase the volume, my pressure is going to go down. So, quick review of Chem 101, Chapter 5. I know that pressure is caused by collisions of the gas molecules with the sides of the container. So if I increase the volume, my container is larger, there's fewer collisions, so the pressure goes down. So I know my pressure, oh my goodness, my pressure goes down. So how do I get back up to my equilibrium pressure? Well, I need to add more moles of gas. Well, which side has more moles of gas? I can see my products have more moles of gas, so I need to then shift to the right to make more moles of gas to reestablish my equilibrium pressure. So we can think, if you increase the volume, goes to the side with more moles of gas. What do you think happens if you decrease the volume? Well, decreasing the volume, smaller container, more collisions. How do I get down to my equilibrium partial pressure? Well, I would go to the side with fewer moles of gas. So again, if you increase the volume, your reaction shifts to the side with more moles of gas. If you decrease the volume, shifts to the side with fewer moles of gas. How about if I add PCl3? So PCl3 is my product. If I add more product, I've got too much product, so what's going to happen? I need to use up that product. How do I use up product? I shift to the left. And we'll have another practice exercise in a few slides, and there's many practice exercises in your textbook, and you have a whole section on Le Chatelier and Mastering Chem, so there's lots of chances for practice here. Quick summary. Increase the volume, shift the side with more moles of gas. Decrease the volume, shift the side with fewer moles of gas. You're only looking for your gaseous reactants and products. Lastly, temperature is decreased. It only shifts to the left if it's endothermic. So by decreasing the temperature, you shift towards the side with heat. By increasing the temperature, you can imagine if I increase the temperature, I'd have to shift away from heat, so shift to the right. If the reaction was exothermic, delta H would be negative, heat would be a product, and if you added heat, it would shift left. If you removed heat, it would shift to right, again for exothermic. So you cannot just memorize if you decrease temperature, it goes left. That's only true for endothermic. So when temperature changes, add heat to either the reactant or product side based on the reaction being endo or exothermic, and then treat heat and temperature as a reactant or product. Okay, so here we have an example of the Haber process, which is the reaction of nitrogen gas and hydrogen gas to make ammonia gas. So this is a graphical description of Le Chatelier's principle in action. So here I know I'm at equilibrium right now. I've got time, partial pressure. I know I'm at equilibrium because my concentrations are not changing, right? So their values are plateaued. That means I've reached equilibrium. And I can see at this moment in time, H2 shoots up. That means I've injected or I've added hydrogen to my reaction vessel. So that's the disturbance. So if I add H, what happens? I've got too much hydrogen. How do I get rid of the hydrogen to reestablish equilibrium? I'll shift to the right. So if I add hydrogen, it'll shift to right to reestablish equilibrium. By shifting right, you're making more products. And looking at NH3, after the disturbance, I see that partial pressure is going up. If I'm shifting to the right, I'm using up nitrogen. So I can see my nitrogen, partial pressure, goes down. After that H2 has been added from that new value, again shifting right, you're using hydrogen, and that partial pressure also decreases. So this is just a way of graphically seeing what happens. We're at equilibrium. Equilibrium is disturbed. The system shifts to reestablish equilibrium. I know equilibrium is reestablished at this point because, again, my partial pressures, they're constant. They're not changing. And this is just an example of the setup or the apparatus that would be used for the Haber process. Okay, so here is, and this is a reaction we'll see in lab, this is a test tube containing this purple solution. And from this diagram, I see purple is COCl4. So let's emphasizing. I made this purple font. Let me write purple in case the color doesn't come across on your screen. Purple. This hexa aqua cobalt 2 ion is pink. Goodness. Okay, purple and pink. So when I'm at room temperature, I have mostly purple solution. That means I've got this tetrachlorocobaltate 2 ion. And I put it in a warm water bath, and I can see it's even more purple. I have fewer pink molecules. I put it in an ice bath, and the solution is pink. So this is a really interesting equilibrium reaction because the products and the reactants are different colors, so you can observe that change. So let's think about this. The reason adding ice, an ice bath, or adding a hot water bath, you can observe a change. That means that the reaction must be endo or exothermic to the point where by adding or removing heat, you can observe a color change. So let's think about this. If I add ice, my solution turns pink. Adding ice is removing heat. So if I remove heat and the system shifts to the left, where does heat go? Well, if you're removing something, that means you have too few of it, you need to make more of it. So that tells me that heat must be a reactant. If heat is a reactant again, that means it would be endothermic. So let's make sure. Let's double check. So by adding an ice bath, I'm removing heat. If I remove heat, the reaction is going to reestablish itself by shifting to the left to make more reactant, which is indeed pink. So that makes sense. Let's check the hot water bath. So if I add heat, the reaction shifts to purple. So if you add heat, you have too many reactants. It's going to shift to the right to make more products, and we see purple. So this is interesting for two reasons. One, by adding or removing heat, you can observe the color change because our reactants and products are different colors. And this is a way you can experimentally determine if a reaction is endo or exothermic. Okay, practice exercise 13. I want to make a slight modification. Let's make this a negative value. So on your notes, make that negative 508. So because I want to have a different example from the previous practice exercise. Negative 508 means we have an exothermic reaction. If I'm exothermic, that means heat is released, and that means I can consider heat a product. And again, I'm modifying this so that in one practice exercise, you have an endothermic reaction, and one practice exercise, you have an exothermic reaction. So determine how the equilibrium constant for the reaction should change with temperature. Okay. Oh, my notes went away. That's annoying. So one more time. Exothermic, negative. That means heat is a product. So I want you to pause the video, think about this. Again, the question is asking, how is the equilibrium constant, which is our capital K, how will it change with temperature? Remember, K is products over reactants. So give that some thought. Pause the video. Once you've thought about it, come up with an answer, then we'll discuss it together. Okay, thank you for pausing. So now, how does the equilibrium constant for this reaction change with temperature? So if I add or if I increase temperature, that means I'm adding heat. So if I add heat, which way will the reaction shift? If I add heat, too many products, shifts left to use up products and make more reactants. So we're going to shift to the left. So if I shift left, I make more of my reactants, and my products If I shift to the left, go down. Apologize for my terrible writing with this mouse. Okay, so if I'm shifting left, and I shift left because it's exothermic, I add heat, shifts to the left, make more reactants, use up products. Remember, K is essentially products over reactants. So if I'm this number, my products over reactants. So if I shift to the left, I'm making more reactants. I'm using up my products. So what happens to that ratio? K will decrease. So again, exothermic, heat is a product. And again, I put this negative sign in here for this example. Heat is a product. If you add heat, it shifts left, so increase temperature. Reaction shifts left, make more reactants, use up products. K is a ratio of products to reactants. So if your number upstairs goes down, downstairs goes up, that K value is going to overall decrease. Okay, and lastly, catalysis. So, what we're looking at with equilibrium, we've got a ratio of reactants to products. That ratio is set by your equilibrium constant. The rate forward equals rate reverse. I have a purple line and a green line. The main thing to realize here, what does catalysis do? So which is the catalyzed pathway, purple or green? Well, the catalyzed pathway will be the one that's faster. Which is the faster pathway? Well, the one with the smallest activation energy. So remember, your activation energy for the green would be from where you start to the top of the hill. For the purple, where you start to the top of that hill. So the smaller activation energy is the green path. That's our catalyzed pathway. So you could see that by adding a catalyst, you increase the rate of both the forward and the reverse reaction. Catalysts, they do not shift the position of equilibrium. They just allow you to reach equilibrium more quickly. Okay, and that does it for 15.9. That is the end of this chapter. Again, you have 2 Mastering Chemistry assignments due on Sunday night, one on Chapter 15, Section 8, one on Chapter 15, Section 9. There are a lot of examples, so please go through those. Work the problems, write notes in your homework notebook. If you've got questions, mark them. Ask questions on Facebook. I'll make an effort to get on, as I always try to, at least once a day to answer your questions. Take photos, take screenshots, really be as interactive as possible and help each other out, and I will go on to check as well.